One of the major reasons we spent so much time talking about how to find maximums and minimums of functions is to solve optimization problems, maximizing revenue, maximizing volume, minimizing surface area. This type of thing is really useful. I'm going to show you step by step how to solve optimization problems, and today we'll do 3 examples. Chapters are in the description if you want to skip around, as well as links to other practice exercises. In our first example, we will maximize the volume of an open top box. In our second example, we will maximize the area of a fenced off region. Our third example is the most difficult. We will find the point on a parabola that minimizes distance to a given point. We could do 1,000 different optimization problems, but the good news is they all more or less follow the same process. Let's begin with our first problem. A manufacturer wants to design an open box having a square base, so the dimensions of the base we could say are x by x, it's a square, and a surface area of 108 square inches, as we see in this figure. What dimensions will produce a box with maximum volume? So our box has a square base, that's x by x, and we'll call its height h. And remember, it has no top. Our first step in solving an optimization problem is to make a sketch if we can. In this case, we already have a figure to use, so we don't have to do any sketching. Then we want to make sure we understand what quantities are given and what quantities we might need to figure out. In this case, we're given the surface area, and this is pretty common in an optimization problem that you'll be given some sort of restriction. In this case, we're trying to maximize the volume given the restriction that we need a surface area of 108 square inches. Since we're given the surface area, we want to write an equation for that quantity. Our surface area is x squared, the area of the base, plus the areas of the 4 sides. Each side has an area of x by h, and there's 1, 2, 3, 4 sides. So x squared plus 4xh is the surface area, and we're given that this has to equal 108. This is called a secondary equation because it's an equation for something that we're not trying to optimize. The equation for what we're trying to optimize is called the primary equation, and that's our second step. We want to write a primary equation, the equation for the quantity we're trying to optimize. In this case, we're trying to maximize volume. So our primary equation is an equation for volume. That's the area of the base, x squared, multiplied by the height, which is h. But we've encountered a problem because this primary equation has 2 variables. In order to use our calculus techniques, we need this equation to be in terms of a single independent variable. But that's where the secondary equations are often useful. This equation for surface area gives us a way that x and h relate. So if we solve this equation for either x or h, just pick whichever one is easiest, we'll be able to use that to rewrite the primary equation in terms of a single variable. And that's the next step. It will be easier to solve this equation for h than it will be for x. So let's solve for h. To do that, we just subtract x squared from both sides, and then divide both sides by 4x. And that gets us here. When we subtract x squared, we get 108 minus x squared. And then when we divide everything by 4x, it becomes 108 minus x squared divided by 4x. And then we just have h on the left side. 108 divided by 4x is 27 divided by x. And x squared over 4x is just x over 4 because a factor of x cancels out. And don't forget we have that negative. So by solving for h and doing a little simplifying, we find that h equals 27 over x minus x over 4. By plugging that in for h in our primary equation, we can rewrite it in terms of a single variable and use our calculus techniques. And that brings us here. The volume is equal to x squared multiplied by h, which we found is 27 over x minus x over 4. Distributing the x squared through the parentheses, we have that the volume equals 27 times x minus 1/4 times x cubed. We're almost done. The fourth step is to determine the feasible domain for our primary equation that we figured out in the previous step. What values for x are possible? Well, we know that x has to be at least 0. We're not going to have negative distances for our box. We also know that x squared has to be less than or equal to 108 by the surface area equation. X squared is in this equation, and the surface area equals 108. So x squared certainly can't exceed that allowed surface area. X squared is less than or equal to 108, which means that x is less than or equal to the square root of 108, and thus this is our feasible domain. X is greater than or equal to 0, less than or equal to the square root of 108. Then we're ready for the final step of using our calculus techniques to find minimums and maximums. In this case, of course, we're trying to find a maximum. And now we know that we're looking for a maximum of our volume V on this closed interval from 0 to the square root of 108, since that's the domain. Because we're on a closed interval, we're really using the extreme value theorem and the candidates test. We need to check the candidates for a maximum. The candidates are the endpoints of this domain, as well as any critical points. Let's begin by just plugging in these endpoints into the volume equation to see what we get. It's quick to see that we get 0 in both cases. If you plug 0 into the volume, well, the volume is x squared times h. So if x is 0, obviously the volume is 0. If we plug the square root of 108 into the volume equation, you can do the math and find that it equals 0, or alternatively, just look at the surface area equation. The surface area has to equal 108. If x is the square root of 108, then the entirety of the surface area is taken up by x squared, which forces h to be 0. If the height is 0, obviously our volume is 0. So these certainly are not going to be our maximums. Let's move on to finding critical points by taking the derivative. Remember, our volume equation is 27x minus 1/4 x cubed. That's what we're taking the derivative of to find our critical points. This is just going to require us to use the power rule. The derivative of 27x is 27, and the derivative of negative 1/4 x cubed is negative 3/4 x squared. So that's v prime, the derivative of our function for volume. This is defined everywhere. So all we have to do to find critical points is set it equal to 0 and solve. Setting it equal to 0 and then adding 3/4 x squared to both sides gets us here. Divide both sides by 3/4 and take the square root. X is equal to plus or minus 6, although of course it's only positive 6 that's in the allowable domain. And now we just have to make our conclusion. By the extreme value theorem, we know that our volume function has to have a maximum and a minimum on this interval. The maximum obviously is not 0, so the maximum must occur at x equals positive 6. And that tells us the dimensions of our box, because remember, we know that the height is equal to 27 over x minus x over 4. And we just figured out that x has to equal 6 in order to get that maximum volume. Thus, we can solve for the height by plugging x equals 6 into that expression, and we find the height is forced to be 3. So the dimensions of the box that will maximize the volume, given that the surface area has to be 108 inches squared, is going to be 6 by 6 by 3, giving a volume of 118 inches cubed. That's how you solve an optimization problem. Here's a look at the guidelines from Larson's calculus before we move on to the second problem. The first thing we did was to identify all given quantities and quantities that we don't know. Make a sketch if possible. In the first example, we were given a picture, so we didn't need to make a sketch. And since we knew the surface area, we wrote an equation for that, called a secondary equation. In step 2, we wrote a primary equation for the equation that is to be optimized. And in step 3, we reduced that primary equation to one having a single independent variable. To do that, we made use of the secondary equations that we wrote in step 1 in order to rewrite the volume in terms of a single variable. Step 4 was to determine the feasible domain of the primary equation. And then step 5 was to just use calculus to find the maximum or the minimum. If the domain was a closed interval, like in our previous case, then we don't have to use the first derivative test or the second derivative test for classifying critical points, because we can just use the extreme value theorem theorem and the candidates test. In our last example, we're not going to have a closed interval, and so we will have to use either the first derivative test or second derivative test. Here is our second example. I think this is from Stewart's calculus. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Here's a few examples of possibilities. You can see that if we use a short and fat design, then we get a pretty small area. And if we get a long and skinny design, we also get a small area. If we go for a more balanced approach, though, the area is much larger. So there's got to be some optimal point, some optimal dimensions for this fenced off area, giving us a maximum area. And that's what we're looking for. We'll begin with a sketch of the situation. We have this river, and then we have our fenced off area. We'll say that the side of our rectangle opposite the river side has a length of y, and then the other two sides that we need both have a length of x. We, of course, are trying to maximize the area of this rectangle. We do have some given information, which is that we have 2,400 feet of fencing. So x plus y, or 2x plus y, will have to equal 2,400. That's all the fencing we have. Now we can move on to the primary equation. Let's write an equation for the quantity that we're trying to optimize. We're trying to maximize area, so we'll write an equation for that. The area of this rectangle is, of course, just x times y. So that's our primary equation, a equals xy. Again, though, we've got two variables here. We need an equation in terms of a single variable. We can fix that pretty easily. This is step 3, by going back to our secondary equation and solving for y. Y is equal to 2,400 minus 2x. And then we can plug that in for y in our area equation to find that the area is equal to x times 2,400 minus 2x, which is the same as negative 2x squared plus 2,400x. Now we have a primary equation in terms of a single variable. The next step is to establish the feasible domain. In this case, x has to be between 0 and 1,200. We obviously can't have a negative dimension on our rectangle, and x has to be less than or equal to 1,200 because the amount of fencing we have is 2,400, and there's 2 copies of x in our design. So x can't exceed 1,200. We don't have that much fencing. So x is between 0 and 1,200. Again, this is a closed interval. Now we're on to the calculus part. We're trying to find the maximum value of this area function on the closed interval between 0 and 1,200. It's easy to see that at the endpoints of this interval, the area would be 0. When x equals 0, the area is obviously 0. And when x equals 1,200, well, the 2x takes up all of the fencing, and so y would be forced to be 0, thus, again, making the area 0. So whatever our maximum is, it's going to be at a critical point. Let's take the derivative of the area function to find the critical point in the interval. We just apply the power rule to find a prime. The derivative of negative 2x squared is negative 4x, and the derivative of 2,400x is just 2,400. Then, since this isn't undefined anywhere, to find critical points, we just set it equal to 0, and that gets us here, x equals 600. And again, we are on a closed interval. We're really using the extreme value theorem here. There has to be a max and a min on this closed interval. The maximum obviously isn't 0, so it must occur at x equals 600. If x equals 600, we know that y must equal 1,200. Just by plugging 600 into this equation. That would give us that 1,200 plus y is 2,400, so y is 1,200. Thus, we have a maximum at x equals 600. The dimensions of the region that we need are 600 by 1,200, and the area that we get is 720,000 square feet. That's the maximum area this region can have, given that we only have 2,400 feet of fencing. Now on to the final and most difficult problem. We want to find the point on the parabola y squared equals 2x that's closest to the point 1, 4. So we're trying to minimize distance. closest, right? We're minimizing distance. Let's begin with a sketch. Here's the xy plane, and we want to graph y squared equals 2x. Y squared equals 2x looks a lot like y equals x squared, except instead of opening along the y-axis, it opens along the x-axis. The specifics of the sketch aren't too important. And let's say the point 1, 4 is maybe right here, and we're trying to minimize the distance between the parabola and this point, or rather, we're trying to find the point on the parabola with minimum distance. Any point on this parabola has some distance from the point 1, 4. We're trying to find which point is closest. So let's just sketch a point on the parabola, say it has coordinates x, y. The distance between a point xy on the parabola and 1, 4 is what we're trying to minimize. We'd also want to write our secondary equation, if there was one. There is one, but it's already written for us. Y squared equals 2x. That relates x and y, and that's going to come in handy for writing our primary equation, which is the equation for distance. This is the distance between any point xy on this parabola and the point 1, 4. It's the familiar distance formula. We have the square root of x minus 1 squared, that's the difference in the x coordinates, squared, plus y minus 4 squared, the difference in the y coordinates squared. Again, this is just the distance between an arbitrary point xy on the parabola and the point 1, 4. To put this equation in terms of a single variable, well, we know that y squared equals 2x, which means x equals 1/2 y squared. So where we had x, we'll just put 1/2 y squared, giving us this equation for distance in terms of a single variable. We could move forward using this square root function for our distance. However, the distance we know is going to be positive, right? The square root always gives a positive number. And x squared, or we could say d squared in this case, is increasing whenever d is greater than 0, which means wherever d squared is smallest is also where d is smallest. So the minimum of d, which is what we're looking for, will also be the minimum of d squared. So it'd actually be easier if we just worked with d squared. That way we don't have to deal with the messy square root. So we'll call our function f of y. What f of y is d squared, which is just the distance function, but without that square root because we squared it. Again, the idea is that wherever d squared is minimum, that's also where d's minimum occurs. So this one will be easier for us to find because we don't have to deal with the square root. We also need to identify the domain of our function, the allowable values for y. In this case, y could be anything from -infinity to +infinity. This is a geometric situation, so there's no real-world restrictions. Y could be anything. Since we're not focused on a closed interval, we will have to use the first derivative test or second derivative test to classify our critical points as minimums or maximums. We, of course, are looking for a minimum. But let's get to it. We'll take the derivative of f of y, and then we can find our critical points. To take the derivative of this, we're going to have to use the chain rule. And that gets us here. The derivative of a thing squared is just 2 times that thing. But then we need to multiply by the derivative of the inside function. The derivative of 1/2 y squared is just y. Then the derivative of y minus 4 squared is similar. The derivative of a thing squared is 2 times the thing, multiplied by the derivative of the inside function. In this case, that's just 1. Now, if we simplify this, we end up getting y cubed minus 8. That's because 2 times 1/2 y squared is y squared, multiplied by y gives us y cubed. But then 2 times -1 times y is -2y, which cancels out with that plus 2y. But then also we have 2 times -4, and that's where we get the minus 8. Y cubed minus 8 is defined everywhere, so the only critical points will be where this equals 0. Setting it equal to 0, we find that y equals +2. Now this could be a minimum or a maximum. We don't have the extreme value theorem to apply here. We don't have a list of candidates. So we do need to classify this using the first or second derivative test. You could also just use some geometric intuition and say, hey, this parabola goes on forever. Obviously, there's not going to be a point on it with a maximum distance from this fixed point. but let's just use calculus. The geometric intuition assures us that y equals 2 is a minimum, and the calculus confirms it. If we take the second derivative to assess the concavity, the second derivative is 3y squared, which is going to be positive at y equals 2. Thus, the function is concave up, and so indeed we've found us a minimum. So the distance between the parabola and the point 1,4 is minimized when y equals 2. What's the x-coordinate there, though? Well, since y squared equals 2x, when y equals 2, x is forced to be 2. So the point on the parabola closest to 1,4 is the point 2, 2. And that's how you use calculus to solve optimization problems. Again, here are the steps. The first step is to identify the given quantities and the quantities you want to find out. Make a sketch if you can and write those secondary equations. Step 2 is to write a primary equation for the quantity you're trying to optimize. Step 3 is to reduce that primary equation to one having a single independent variable. Usually we have to do this using the secondary equations. Step 4 is to determine the feasible domain of our primary equation, and then step 5 is to just use calculus in order to find the max or the min. Let me know in the comments if you have any questions. You can check the description for links to other problems as well as my calculus playlists, and if you find these videos helpful, please consider supporting Wrath of Math on Patreon. There's a link in the description, and it'd be a huge help. You can get early access to videos as well as access to my PDF notes like this one.
Persistence, couldn't even open myself up for an instant. What's the law? It's regular. I regulate my integrity. I'm a secular anesthetic from my own effigy. I didn't try just to be